Hey folks, my name is Nathan Johnston, and welcome to our first lecture video on vector calculus. We're going to do somewhere in the ballpark of 35 to 40 lecture videos in this video series, and we're going to cover the entirety of our vector calculus course. So if you're here at Mount Allison University, this is what we call Math 3141, vector calculus. But if you're at another university, it's probably roughly equivalent to what you would call Calculus 4 at your university, okay? So the intended prereqs here are that you've taken two first-year calculus courses, usually differentiation and integration of single variable functions, and then a follow-up calculus course on multivariable calculus, like calculus on surfaces. And now we're in the fourth calculus course, vector calculus, calculus of vector valued functions. Okay, so let's get into it. This course here, we're going to be using the textbook Vector Calculus, the 5th edition of it, by Susan J. Colley and Santiago Cañez. Okay, so let's get into it. Let's learn about vector calculus. And maybe before we do that, let me remind you a little bit about some things that you've learned in previous courses, or some types of objects that you've learned how to deal with previously in earlier calculus courses, okay? Because we're going to be building off of these things. Okay, so back in your first two calculus courses, you learned how to deal with functions from R to R, right? The set of real numbers to the set of real numbers, okay? That was single variable calculus. You learned how to take derivatives. You learned how to compute integrals, those sorts of things, okay? And then you ramped up when you got to multivariable calculus. You learned how to take derivatives and do calculus-y sort of things with functions from Rm to R. Okay, so now you had like M input numbers, or equivalently, you could think of this as you were plugging in a vector with M entries into the function, but you still got a real number out. The output space was still one-dimensional. Okay, and you learned how to do calculus in that sort of setting. Okay, and in some courses, you've also learned how to deal with functions from Rm to Rn, okay? If you think back to linear algebra, you learned how to deal with functions that sent vectors to vectors, but only in a very special case. Only in the special case when the function that you're dealing with is a linear transformation. So it has this really nice property that if you feed a linear combination into the function, well, you can just pull that linear combination out. So you can pull out scalar multiples and you can pull out vector addition, and it doesn't screw up the function, basically. Okay, so for those special types of functions from vectors to vectors, you know how to deal with them. Okay, and sort of what we're going to do in this course is we're going to learn how to deal with functions like this. So functions from Rm to Rn, where m and n are arbitrary now, but we don't necessarily have this extra linear transformation restriction down here. Okay, so it's just general functions in that regime. How do you do calculus in that setting? Okay, and these, we call these vector valued functions, right? Because they're taking in vectors and they're spitting out vectors. And we want to know how to deal with these. How do we do calculus on these types of functions? Okay, so how do we deal with functions that have range equal to a set of vectors, right? The set of outputs of this function are vectors, and they're not linear transformations. How do you deal with those? Okay, so that's sort of the goal here. Now we've got some function, it's not linear, okay? So like if you sort of were to graph it or whatever, like it doesn't look like a line or a plane or a hyperplane or anything like that. It's a curvy thing. Well, that's where calculus shines, when you've got curvy things. So how do we do this? Okay, and in our first lecture, we're going to dumb things down a little bit, okay? We're still going to look at something new that we haven't looked at before, but we're going to dumb it down to sort of the simplest case of something that we haven't looked at before, okay? We want to deal with these functions from Rm to Rn. We're going to start with the m equals 1 case, which we haven't done yet, okay? We've dealt with, n equals 1. That was multivariable calculus. But what about m equals 1, okay? So we're just plugging in a number to the function, and we get out a vector. What can we do with those sorts of functions? So let's start there before we ramp up to arbitrary m, okay? And so this is our first definition, okay? That's sort of the idea here. We've got a function that's going from some interval, okay? So it's just some interval in the real line, so it's a one-dimensional thing, but it's spitting out vectors, okay? It's spitting out vectors or points in n-dimensional space. And while any function of that type, as long as it's continuous, we call it a path, okay? And so let's talk about this a little bit, okay? So like, let's try to understand this definition a little bit better, okay? And so first off, when I say an interval, like what is an interval here? Well, it's what you would expect, okay? An interval, for example, it might be a set of the form AB, right? Closed brackets, so including both endpoints. That's an interval, okay? Maybe it doesn't include its endpoints. Maybe it's from A to B, but with round brackets, so it's everything between A and B, not including the endpoints. Or you can mix and match in lots of different ways, right? You might include one endpoint, the A, but not the B, or maybe you have an interval that's going off to infinity on one side, or maybe even on both sides, maybe on just the other side, and then it's not including B on the right-hand side. There are lots of different intervals that you can write down. The point is, you know what an interval is, okay? Any of these things are fine and dandy as the domain of a path. Any interval, it doesn't matter what it looks like whether it's infinite on one side or both, and whether it includes the endpoints or not. Fine, don't care. Okay. And another thing that I want to clarify here a little bit is what do we mean when we say that it's a continuous function? You know what a continuous function from the set of real numbers to the set of real numbers is. You learned how to deal with that back when you talked about limits for functions of one variable, right? A continuous function of one variable, it's one where if you wiggle the input around just a little bit, the output also just wiggles around a little bit. Okay, and what we're going to do here, okay, for functions that are going from a one-dimensional space to an n-dimensional space, is we're going to say that it's continuous just if each of its components is continuous, okay? And that lets us leech off of things that we already know, okay? So we say this f here, this vector-valued function f, it's continuous if, well, okay, let's think about this. This f here, this vector-valued function f, its output is n-dimensional, okay? So in other words, I can think of that as there are n entries in the output, okay? So another way to think about a function like this, another way to think about a path, is it's a function that takes in one real number t, and it spits out n real numbers, f1 of t, f2 of t, all the way up to fn of t, right? Just give names to the n different components in the output. And what that lets you do is it lets you think of each of the entries as a one variable function, right? I can think of t is being transformed by some function into the first entry of this output vector, and that's being transformed by some other function into the second entry of the output vector, and so on all the way down the line. Okay, and this is really useful because it lets us leech off of things that we know about one variable functions to conclude things about paths here. And in particular, what I mean by a continuous function from an interval to a set of vectors is just, well, each of these functions here, f1, f2, up to fn, each of those has to be continuous, okay, in the one variable function sense. Okay, so fine and dandy. So that's a path. Why is it called a path, though? It's a function. Why is it a path? A path is sort of a very geometric name. And so let's do some examples to try to get some intuition for this, okay? Sort of the idea is that this is a function from real numbers to a larger space. And we're going to sort of be able to think about it as okay, we're going to think of the input variable. We're going to call that t, and we're going to think of it as time. And then there's some vector in the output space that's just moving around and tracing out some curve as time goes on, okay? And that's sort of where this path idea comes from. Okay, so anyway, so let's do a bunch of examples of this, okay? We can visualize them at least when n equals 2 or n equals 3, so the output space is two-dimensional or three-dimensional. Let's start with a two-dimensional example, okay? So suppose that we've got two fixed two-dimensional vectors, a and b, and a is going to be non-zero, just otherwise things get a little degenerate and harder to picture here, okay? And now I'm going to define a path in this way, okay? I'm going to say, okay, yeah, there's one input variable, call it t, because I'm going to think of it as a time. Okay, and then the output is going to be t times a plus b, okay? And what does this look like? How can I visually think about this path? Okay, and so I'm going to draw the output space, okay? My typical way of sketching or visualizing a path is I'm just going to draw the output space. I'm going to think about how it changes over time. And okay, so first off, if t equals 0, then this t times a goes away, right? And I'm just left with an output of b. I don't know what b is. B is just some vector. I haven't been told which b it is, but b is some vector. So when t equals 0, yeah, the output is here, okay? It's the vector b, okay? Now, what happens as I change t? Okay, so for example, when t equals 1, okay, now I've got 1 times a, so just a plus b is the output. Okay, and remember, a plus b, if you think back to linear algebra, where that vector is, well, if I follow the path of b and then follow the path of a from there, then I end up at a plus b. Okay, so if I sketch some vector a, starting at the head of b and then going wherever a goes, then at the end of that path, I end up where I am at t equals 1. Okay, and now just sort of fill in the dots, okay? When t equals 0, I'm down here. When t equals 1, I'm up here. Well, when t equals a half, I'm going to be halfway in between. When t is bigger than 1, I'm just going to continue going up in that way. When t is less than 0, I'm going to go down this way. Okay, so sort of what's happening here is this path, I can think of it as this straight line that's in the direction of A. It's just going whatever direction A goes, but it's not going through the origin or anything like that. Where it's sort of situated in space is it goes through the head of B. Okay, so that's how we can think about this. Okay, this path here, it's the straight line going in the direction of A, going through the head of B. Okay, and furthermore, I'm always going to indicate which way my paths are going. Okay, because there's sort of a direction of movement here. Okay, I'm thinking of t as time increases. Okay, so I'm sort of imagining here that there's some particle on this line that's traveling this way. So that's why I've got these arrows here to sort of indicate the direction that the line's moving. It's going in the same direction as A, not the opposite direction. Okay. All right, and I should note that, even though we've drawn the picture here in 2 dimensions, this works exactly the same in higher dimensions. You have this exact same interpretation. If you have this function, except A and B, they're not in R2 anymore. Maybe now they're in R3 or R7 or whatever dimension you like. Okay, still, this formula here gives you a straight line, in the direction of A going through the head of B. Okay. Let's do another example. Instead of sketching something in 2 dimensions this time, let's look at something in 3 dimensions. Okay, so suppose that you've got real numbers this time, A and B. Again, they're not told to me. Okay, they're just parameters. Okay, but suppose that A is positive and B just is whatever it is. Let's sketch the path. This time we're going to be sketching something in 3 dimensions. Sketch the path that's defined by this formula here. Okay. And this path here, I mean, if we go back a little bit, remember when I was talking about continuity, I said every path, you can sort of write it in terms of the components, F1, F2, up to Fn. Well, here n is 3, and we've done that very, very explicitly. I've told you how each of the 3 components are changing as time changes, as the input changes, okay? So like what I called F1 before, that's A times cos t. F2 is A times sine t, and F3 is B times t. Okay, what does that path look like? Sort of geometrically, what shape is it carving out? Okay, and the first thing that I want to notice, okay, to try to get my head around this is if I only looked in the xy plane, okay, so if I only looked at the first 2 coordinates, and I ignored the third coordinate, ignored the b times t altogether, then, well, that looks like a circle to me, right? I mean, this A times cos t, A times sine t, like that's just how we, like if A was 1, that's just how we parameterize the unit circle usually, right? And then multiplying both of them by A, that just makes it a circle of radius A now. Okay, so in the xy plane, in other words, like this is a 3-dimensional shape, but if I look down at it, look just at the floor, look at the xy plane, I only see a circle. I see a circle of radius A. Okay, but now like let's take the z coordinate into account. Okay, as t increases, okay, well, let's suppose for a second that b is positive. Okay, then as t increases, b times t is going to increase. Okay, so what I'm sort of visualizing here is I've got a particle going around and around, but as time goes on, it's also going up. Okay, or similarly, if b is negative, okay, now the particle is going around and around, but as time goes up, b times t is going down. Okay, so I've got this particle spinning around, but it's going down as it spins around. Okay, that sounds an awful lot like a helix to me. Okay, that's what I think this probably looks like, a helix or a spring or something like that. Like imagine taking a slinky and just sort of stretching it out. Okay, and it turns out, yeah, that is what you get. Okay, like if b is positive, then you just get this particle that's going up and around and tracing out this helical path. Okay, and the parameter a, that just specifies how big around this helix is, and the parameter b specifies how squished together or stretched out the spring or helix is. Okay. All righty, let's do another one. All right. And we're going to go on to, sort of a weirder one now. Maybe that's one that's a little bit harder to get our heads around. Let's talk about this path, okay? So again, like the entries of the path are given to us very explicitly. I've just given you formulas for the first entry, F1, and I've given you a formula for the second entry, F2. And so the claim is that this path here, the claim is that it traces out the unit circle, except it never hits the leftmost point of the unit circle. It traces out all of the unit circle except for that one point. It misses that one point. Okay. So how could we convince ourselves that this is actually true? Because I mean, this looks very, very not obvious, right? Like if the entries were cos of t and sine of t, then you say, oh yeah, unit circle. That's not what's going on here. Here I've got some other parameterization of the unit circle. How can I really convince myself that it is tracing out the unit circle, again, except for this point? Okay, and there are a couple ways that you could approach this, but the way I'm going to do it is I'm going to notice that, okay, if these points really are on the unit circle, then when I take the x-coordinate and square it, and then I add on the square of the y-coordinate, I better get 1. Okay, so that's what I'm going to try to do first off. Okay, I'm going to start not necessarily by showing that this reaches every one of those other points on the unit circle, but at least that every one of these points is on the unit circle. Okay, so here, like, this is just the x-coordinate squared, this is the y-coordinate squared. If all these points are on the unit circle, this had better evaluate to 1. So let's just double check that that actually is the case. Let's just do some algebra, right? When I square out this numerator over here, I get 1 minus 2t squared plus 4, 1 minus 2t squared plus t to the power 4. And then over here, when I square that out, I get 4t squared. And on the bottom, I've got the same denominator on both of them. So I've written it with a common denominator. It's just 1 plus double the cross term plus t to the power 4, because that's t squared squared. Okay, so this is what we get. And wouldn't you know it, minus 2t squared plus 4t squared, that gives you a plus 2t squared as your new cross term. And now the numerator and denominator are exactly the same. So yeah, you get 1. Okay, every single one of these output points is exactly a distance of 1 away from the origin. So they're all on the unit circle. Okay, great. We're not done yet. That shows me all these output points are on the unit circle. It doesn't show me that, I get every point on the unit circle except for -1, 0, though. Okay, so how do I do that? Okay, and maybe the first thing that I should do is convince myself that I really don't get this point. Okay, in other words, convince myself that there's no value of t that I could plug into this function to get this as the output. Okay, so let's imagine what would happen if I plug in a value of t into this formula on the right-hand side. And let's suppose, okay, what happens when my y value, when my second coordinate is 0? How can that happen? Okay, well, the only way that can happen is if t is 0, right? Because I need the numerator to be 0. The only way that can happen is if t is 0. Okay, so if this point ever is reached, it must be at t equals 0. But what happens in the x-coordinate when t equals 0? If t equals 0, then you've got 1 minus 0 over 1 plus 1. Oh, that's just 1 in the first coordinate. In other words, we don't get the point -1, 0. The only point that we get that has a y value of 0 is 1, 0. In other words, we get the rightmost point on the unit circle, but not the leftmost point. There's no value of t that we can get, that we can plug in to get the leftmost point on that unit circle. Okay, fine. So we don't get that leftmost point. How do we know we get every other point on the unit circle, though? Okay, and the trick here is, let's consider limits. Okay, because I'm getting closer and closer points to that point -1, 0 without ever hitting it, that seems like a limity sort of thing. So I'm going to ask, okay, what happens as I go all the way to the left in this domain, the real line? So in other words, what happens as t goes all the way to -infinity? And then I'm going to do the same thing all the way to the right. What happens as t goes all the way to positive infinity in that domain? Okay, and let's just compute that. Okay, what happens to this function f of t as t goes to -infinity? And I mean, this is first year calculus stuff. You know how to compute these limits. Just compute the limit of each entry. Okay, if you like, you can think of this as you take the leading coefficient divided by the leading coefficient, right? The quickest growing thing in the denominator is t squared. So look at the coefficients of t squared in the top and bottom. You get -1 over 1, so you get -1 in that first entry, and you get 0 t squared divided by 1. Oh, you get 0 in the second entry. Okay, so as t goes to -infinity, you're getting really close to that point, -1, 0. Remember, you never actually hit it, though, but you get as close as you like. Okay, and it's important here to notice that, okay, if t is going to -infinity, then this y-coordinate, it's always negative here, okay, right? You've got 2t on the top, something positive on the bottom, so the whole thing is negative. So yeah, it's going to 0, but it's going to 0 from underneath. Okay, so sort of what happens when t is going to -infinity, you're tracing out the portion of the circle that's really close to the point -1, 0, but underneath of it. Okay, so that's the portion of the unit circle that you're getting. Okay, so yeah, from below, let's do the same thing as t goes to infinity, positive infinity this time, okay? And the limit calculation works out the exact same, okay? You're still approaching the point -1, 0. The only difference this time is this time the y-coordinate's always positive. This time t is going to positive infinity, so it's a positive number. You've got a positive divided by a positive. Oh, that whole y-coordinate is positive. Okay, so this time, this limit, it's the same point, but it's approaching it from above. Okay, and now to stitch this all together, Remember that paths by definition are continuous. So this function here, f, I mean, you can also just check directly that it's continuous. Okay, so like both of the entries are continuous. So when I trace out this curve, okay, all of the points are on the circle. I've got to, go from just below zero, negative, or sorry, negative 1, 0 to just above negative 1, 0. I've got to do it in a way without lifting my pencil. The only way to do that is to go all the way through the entire rest of the unit circle. Okay, so I really do get that whole unit circle except for that leftmost limit point. Okay, and continuity lets us stitch together the two endpoint behaviors and see that we really do get all of those other points. Okay, it's kind of like an intermediate value theorem sort of argument that we're using there. It's got to go through all of those other points because of continuity. Okay. And now one nice thing about this example is it illustrates that curves can be parametrized by many, many different paths. Okay, you can have lots of different paths that look very different on the surface, but trace out the exact same curve. So for example, that curve we just talked about, the unit circle excluding its leftmost point, the point negative 1, 0, we could have just traced that out with trig functions, like in a more sort of familiar way. We could have traced that out by the path cos t sine t, where t goes from pi to 3 pi, okay? Excluding the endpoints, okay? If we included one of those endpoints, then we would actually get that leftmost point. But because we're excluding the endpoints, it goes from, that leftmost point around the circle, not touching the leftmost point, but goes right from it, almost touching it, all the way around, and again stops just before touching it. It would trace out the exact same curve. Okay. And sort of for this reason, because there are multiple different ways of tracing out a curve, right? There are multiple different paths that do the job for us. We're going to try to be careful to distinguish between what we call a path and what we call a curve. Okay. These are two slightly different things. They're very related, but they're different. Okay, so a path, we talked about these already. I gave you a formal definition of what a path is. And just to remind you, a path, it's a function. Okay, it's a function from some interval to, an n-dimensional space. And sort of the point here is it's a function, which means it changes. It's dynamic. Okay, you can plug in some time and you get an output vector. And then you plug in some other time and you get a different output vector. As the input increases, the output changes. Okay, so it's a dynamic thing. Oftentimes we think of it as a particle moving through space. Okay, and that particle traces out a curve. The particle is not the curve itself. The particle is a moving dynamic thing. The particle is the path. Okay. On the other hand, the curve is the range of the function. It's what happens if you plug the entire domain, the entire interval I, into the function. Okay. And it's not something moving through Rn. This is a subset of Rn. This is the curve that is traced out by that particle. It's the curve that's traced out by the path. Okay. This is the range of the function. And in particular, it's not dynamic. Okay. It's static. It's unchanging. It's just the collection of all the points that the particle ever moves through. All right. We'll leave it there. Thanks for watching, everyone. We'll have about, 35 more of these or somewhere in that ballpark. So I will see you lots over the coming weeks. Have a good one.